So we have learned about the MM1 queuing system, and here is the first example to apply what we have learned so far. So in this problem, the first important information is that 10 cars per hour arrive in the queuing system. And then we also notice that the average service time for each customer is 4 minutes. And I think another important information is that this system has only a single server. So there is only one server in this to handle this queuing system. Finally, it says both inter-arrival times and service times are exponential. We have 4 questions to answer, and then there will be a pause in this video to give you more time to read these questions more closely. So first, let us define this queuing system in terms of a Kendall-Lee notation. And here's the notation. The first M is there because it says the inter-arrival times is following exponential distribution. The second M here because it says that the service times are exponential as well. Okay, so that's why we have M. And then this thing here, 1, is because we only have a single server. And then there's no information about the queuing discipline, so we just write GD. And also this system has an infinity capacity to hold all the customers who are coming to the system. And then the population is also large, or it is not mentioned in the problem, so we just say for these 3 parts here, just GD infinity infinity. Okay, so that is the Kendall-Lee notation for our queuing system. And then based on the other informations, we can say that the arrival rate is 10 cars per hour, right? It comes from here, so we just say that is the arrival rate. For the service rate, however, we do not have direct information from the problem because in the problem it says that the average service time is 4 minutes. It doesn't say how many cars per hour can be served by the system. Okay, so notice here that if the arrival rate is having the units of cars per hour, then the service rate also needs to have the same unit. So mu must be in the unit of cars per hour. That's why we cannot use this 4 minutes because the unit is 4 minutes per car. Okay. So actually the 4 minutes per car is 1 over mu. So 1 over mu is 4 minutes per car. So 1 over mu is 4 minutes per car. But first we would like to change the unit into hour. So this is equal to 4 over 60 hour per car. Okay, and that is 1 over mu. And then we just flip it to become mu. So it becomes 60 over 4, and it equals 15 cars per hour. Now you see that both lambda and mu's, they have the same units, cars per hour, customers per hour, and it must be in that unit. Okay, so remember that both lambda and mu, they must be in the unit of how many customers per unit of time. Finally, we can calculate rho, which is lambda over mu, and that is 10 over 15. Now we have prepared everything, and then we may answer the first question. What is the probability that the teller is idle? So when we're talking about probability here, it means that we're going to calculate something related to pi. Okay, because remember pi is the steady state probability in the queuing system. Now let's think about the condition. The teller is idle when there is no customer, right? Because the teller in the system is only one teller. So of course, he or she is idle when there is no customer, right? Remember again, because we only have one teller. So the only way he or she is idle is when there is no customer in the system. What is the probability of having no customer or zero customer in the system? It is pi 0. Now, if you look at the video about the steady state probabilities in MM1 system, this is the formula for pi 0. And then we have got the row here ready. So we know that pi 0 is 1/3. So 1/3 of the time, the teller in the system is idle. Now, the second question asks, what is the average number of cars? So when we're talking about the average number of cars, it must be related to L. Now we see it specifically asks the number of cars waiting in line. So we are going to calculate LQ because it asks about the average number of cars waiting in line, and that is LQ. This is the formula, and then we just plug in the row over there, and we got the answer. 4/3 customers in average are waiting in line. The third question is about the average amount of time a drive-in customer spends in the bank. So when we're talking about time, it is about W. And then here it says spends in the bank. It means that whether the customer is waiting or the customer is being served by the server, it doesn't matter. It is included in all this average amount of time. So what we're going to calculate is just W, because again, here it says a drive-in customer spends in the bank. So this is the formula for W. We just plug in the mu and lambda, and then we got the W is 1/5 hour. Now the fourth question is not very direct. It asks how many customers per hour will be served by the teller. So let's make an observation. Suppose the teller is constantly busy all the time. The teller is always busy serving customer. Then we can say that the teller must be serving 15 customers per hour, right? Because the teller is always working all the time serving customer. But that is if the teller is constantly busy. From the first question, we know that the teller is idle 1/3 of the time. It means that the teller is only busy 2/3 of his time. Now, if the teller is always busy, then he or she can serve up to 15 person per hour. Now we know that the teller is only busy 2/3 of the time. It means that the teller only serves 2/3 of that amount, which means that the teller on average serving 10 customers per hour. So that's all for this example, and we're going to look at another example in the next video. So see you in the next one, and thank you.